For our senior design project, we chose to examine the problem of resource distribution to counter the spread of epidemics. Our project aims to build off of previous research to apply a model for cost-optimal distribution of resources throughout a networked population given a fixed budget to best constrain the spread of disease. Our team has implemented a conic geometric program to control infected susceptible viral spreading process taking place in a directed network of major U.S. cities. We have built our model using disease spread data from Google Flu Trends along with corresponding contagion parameters. The goal of the project is to create a policy tool that can be used by both researchers and health organizations to maximize the containment of diseases under a fixed budget. In our resource allocation model, P of t represents the portion of the population infected in time step t, and the delta i's represent the recovery rates for each city. The convex optimization function aims to minimize the eigenvalue, lambda, of the matrix M, which represents the bidirectional relationships between cities. Minimizing lambda essentially maximizes the recovery rates for each city in the network. This minimization problem is constrained by two key factors: the total budget input by the user and the range of possible recovery rates. Allocating more resources to a particular city will increase the recovery in that city up to a specified maximum. The cost function depends on the natural and maximum recovery rates for each city as well as the city populations. We assume that the amount of resources necessary to increase the recovery rate in a particular city is dependent on population size. Once the resource allocation problem is solved, we are able to graph the improved results by comparing the proportion of the population that would be infected after the additional resources are supplied with the original data. At first, we use the following simplified formula to predict the infected populations at the next time step. We have now implemented the full predictive model in our web app. The full mathematical model shows the relationship between each city's proportion of the population infected at a time step, the city's recovery rate, and the relationship weights between cities. The natural recovery rates were calculated by minimizing the distances between the original data curves and the predicted data curves when $0 budget is allocated. For example, the 2009 Philadelphia predicted and actual curves are shown here based on $0 in additional resources. Our website now also dynamically returns the results of the resource allocation. After exploring many methods of connecting our website to the MATLAB code, our final solution involves signing up for a Ubuntu server with a company called DigitalOcean. After some small hurdles uploading MATLAB to the server, we are now hosting the website on a domain, seniordesign-goingviral.com. Given that the goal of our project is to be a public policy planning tool, we decided to seek out public health professionals at Penn to get their feedback on our website. Through these meetings, we were able to better understand website features that would be helpful for the user, such as showing data about age distributions of cities, providing the user with suggested networks in the heat map, and presenting resource allocation results in a tabular form. They also helped to identify non-intuitive features of our website so that the current version is much more visually appealing and user-friendly. This is the homepage where you will find information on our team and advisors, as well as the background information about our project. On this tab, you can graph the proportion of the population infected by the flu out of 100,000 people in particular cities during a selected flu season. You can also graph multiple cities on the same graph to compare the trends. Demographic information on age and gender breakdown for the cities is also available at the top of the page for the user to better interpret the data. This tab allows users to visualize the correlations between the flu data of cities in a network over a given period of time. The user can select cities on their own or choose to look at a pre-selected set of related cities. The resulting heat map will show how correlated the flu trends are for the cities in the selected network based on the sizes of the circles over each city. The exact influence value for each city can be found by clicking on the circle. These values increase as a particular city's data becomes more strongly correlated with that of other cities in the selected network. Finally, the main portion of our website is the resource allocation tool. Users can input their budget into the site, select a region in a flu season, and see the results of the resource allocation after submitting. The chart displays the optimal budget allocations to each city in the network, the natural and improved recovery rates for each city, the number of people saved, and the average cost per life saved. Below this information, the user can graph a particular city to compare the infected populations if the resource allocation were applied compared to allocating no additional resources. The red graph depicts the number of people infected without the resource allocation, and the blue graph shows the results of the allocation.